pink granite boulders, salt-stiffened scrub, cold southern ocean water, and a sealed road tracking west into what looks like an empty horizon. Stand at the edge of the Southern Ports Highway outside Beachport and you see sand, low limestone ridges, and grazing paddocks running flat to the Southern Ocean. It looks settled, quiet, and geologically dead. The youngest volcano in Australia erupted right behind this coast just 5,000 years ago. What is remarkable about this landscape is not that it is volatile, but how thoroughly that volatility was overlooked. For more than a century of European pastoral settlement, the flat coastal plains of southeastern South Australia and western Victoria were treated as permanently dormant scrub and swamp. In passing, pastoralists and surveyors saw only stony rises and rich soil. They built homesteads inside craters and drained swamps between ash cones without recognizing that the volcanic field underneath them is alive. How did a volcanic belt stretching 400 kilometers across 2 states escape being recognized for what it is? And what does its underlying anatomy mean for the settlements sitting on top of it today? For generations, the standard geological assumption across the Australian continent was that tectonic activity had essentially ceased in the deep past. The continent is famously an intraplate shield, ancient, weathered, and stable, sitting thousands of kilometers away from any active subduction zone or oceanic spreading ridge. In this part of the country, that assumption seemed entirely logical. The ground between Melbourne and Mount Gambier is not broken by jagged alpine peaks or steaming vents. The relief is gentle, consisting of coastal plains, dune ranges, and low-relief basalt rises. Early settlers saw excellent agricultural ground, black volcanic loams, and abundant groundwater, assuming the underlying limestone and basalt were relics of an epoch long before human history. The first crack in that comfortable certainty appeared in the late 19th and 20th centuries as geologists began mapping the true age and distribution of the Newer Volcanics Province. This volcanic field covers roughly 15,000 square kilometres across western Victoria and southeastern South Australia, containing more than 400 distinct eruption centres, maars, and scoria cones. When radiometric dating and sediment cores from crater lakes were analysed by researchers, the timeline compressed dramatically. The province did not shut down millions of years ago. Activity had pulsed steadily from the late Tertiary straight through the Quaternary, culminating in intense, explosive phreatomagmatic eruptions at Mount Gambier and Mount Shank within the last several thousand years. The traditional owners of this country, including the Boandik and Gunditj Mara peoples, had never lost track of the heat in the ground. Their oral traditions explicitly recorded the fire, ash clouds, and earth tremors of these young eruptions, long before colonial geologists mapped the basalt. The official record, however, had to reconstruct the mechanism from scratch. The puzzle of this landscape is why a continent far from any plate boundary continues to melt at its base, pushing magma through hundreds of meters of water-saturated limestone, and what happens when that volcanic plumbing intersects the everyday towns, roads, and aquifers built across its surface. The sequence that built this volatile corridor did not start with fire, but with water and stretching continental crust. Around 95 million years ago, during the late Cretaceous, the supercontinent Gondwana began to tear apart. Australia started uncoupling from Antarctica, opening a vast rift basin along what is now the southern margin of the continent. As the rift widened and seawater flooded in, marine sediments accumulated across hundreds of millions of years. This created the Otway Basin and the Gambier Embayment, thick sequences of porous Gambier limestone, marl, and sandstones that today form the shallow, water-bearing strata of the region. By the time continental separation was complete, roughly 45 million years ago, the Australian tectonic plate had begun its isolated drift northward into the Indo-Australian plate boundary at roughly 7 centimetres every year. That northward drift is the engine behind the entire volcanic field. The standard textbook explanation for volcanism requires a tectonic plate boundary, where one plate dives beneath another or 2 plates pull apart. Australia sits firmly in the middle of its plate. The Newer Volcanics Province is an intraplate volcanic province, a category of geological feature that took decades of debate to properly explain. The triggering condition lies directly beneath the continental lithosphere. As the Australian plate glides north, the underlying mantle experiences subtle upwellings and edge-driven convection currents. Where the lithosphere thins along the passive southern margin, decompression melting occurs at depths between 60 and 100 kilometers. Magma accumulates in the upper mantle, waiting for a structural weakness to breach the crust. That breach began roughly 4.5 million years ago in the Pliocene epoch, and it has not stopped. The province evolved in 2 distinct geological expressions. Across the central plains of western Victoria, extensive basaltic lava flows poured from fissure vents and low-shield volcanoes, spreading fluid sheets of basalt over thousands of square kilometers. This created the vast volcanic plain stretching between Melbourne and Hamilton. Further west, in the Gambier embayment near the present South Australian border, the rising basalt magma encountered something radically different. It hit shallow, saturated limestone aquifers charged with immense volumes of fresh groundwater. When rising magma at over 1,100 degrees Celsius meets water-bearing porous limestone, it does not form a quiet lava flow. It triggers phreatomagmatic explosions. The groundwater flashes instantly into superheated steam, expanding by more than 1,000 times its original volume. This rapid expansion shatters the surrounding Gambier limestone and basalt into fine ash, ejecting pulverized rock and molten basalt fragments high into the atmosphere. The resulting craters are maars, wide, low-relief basins excavated deep below the regional water table, encircled by low rims of layered ash and tuff. Blue Lake in Mount Gambier, Valley Lake, Leg of Mutton Lake, and Brown Lake were blasted straight through 30-million-year-old limestone in this manner. For the early colonial pastoralists who arrived in the 1840s, this underlying earth history was completely invisible. Surveyors mapped the fertile black soil, the limestone sinkholes, and the freshwater lakes as pastoral assets, naming features after European figures and establishing sheep runs across the crater rims. The official records categorized the landscape as ancient and extinguished, assuming the volcanoes were inert relics of a primeval past. Yet beneath the quiet pastoral paddocks, the deep-seated structural fractures and mantle thermal anomalies remain entirely intact. The timeline of this volcanic belt was not measured in millions of years, but in thousands, leading scientists to confront an unsettling question. What specific radiometric proof exists that the fires beneath this continent are far closer to the present day than anyone originally believed? The moment the geological timeline broke open came when researchers stopped looking at the volcanoes as weathered topography and started dating the material buried directly beneath the ash. For decades, the standard method for dating basaltic rocks was potassium-argon dating. Potassium-argon measurements across Western Victoria consistently produced ages running into millions of years. The older lava shields near Ballarat and Hamilton tested at 2 to 4 million years, cementing the view that southeastern Australian volcanism was an ancient, dying relic of the Tertiary period. When applied to the youngest glassy scoria cones at Mount Gambier and Mount Shank, potassium-argon returned unreliable results because the rock contained excess argon inherited from the mantle and too little accumulated radiogenic decay. The turning point began in the 1950s and 1960s with the emergence of radiocarbon dating. Geologists from the Geological Survey of South Australia and academic researchers realized that the explosive phreatomagmatic eruptions had not merely deposited basalt. The blast clouds had buried ancient soils, charring coastal vegetation and trapping organic matter under thick blankets of volcanic tuff. Drill cores extracted from the ash aprons around Mount Gambier recovered fossil charcoal samples sealed directly beneath the tuff layers. When these charcoal samples were processed by accelerator mass spectrometry, the results startled the geological community. The radiocarbon dates did not land at hundreds of thousands of years. They landed between 4,000 and 5,000 years before the present. The ash fell while human beings were walking this coast. That discovery triggered a wave of multidisciplinary scientific investigation. To verify the radiocarbon timeline, geoscientists turned to thermoluminescence dating and optically stimulated luminescence of quartz grains extracted from dune sands beneath the lava flows at Mount Shank. The luminescence dates confirmed the timeline, placing the youngest eruptions at Mount Shank at roughly 5,000 years ago. At the University of Melbourne and the Australian National University, researchers extracted sediment cores from the deep floor of Blue Lake and Valley Lake. Blue Lake occupies an explosion maar 60 to 70 meters deep. Core samples revealed laminated sediments, microfossil diatom assemblages, and fine pollen grains layered above the impact ejecta. The pollen records documented a sudden shift in local vegetation. Coastal scrub was abruptly incinerated, replaced by pioneering bracken ferns before the eucalyptus canopy slowly re-established itself over centuries. High-resolution airborne aeromagnetic surveys flown by Geoscience Australia and the Geological Survey of Victoria exposed what the surface soils hid. Magnetic anomalies showed hundreds of buried basaltic dikes, linear fissure swarms, and hidden volcanic conduits crisscrossing the Otway Basin. The volcanic plumbing was not confined to isolated hills. It formed an interconnected network of magma pathways cutting straight through the Gambier limestone. Seismic reflection lines recorded for petroleum and groundwater exploration revealed deep crustal faults that act as vertical chimneys, channeling mantle melt directly toward the surface. In 2014, a comprehensive argon and luminescence reassessment, published in Quaternary Geochronology, demonstrated that Mount Gambier experienced multiple distinct eruptive pulses separated by centuries, rather than a single brief event. The scientific proof was unambiguous. This province is not extinct, but dormant. But what happens when that proven subsurface heat and fracture system intersects the towns, water supplies, and pastoral communities living right above it today? The consequence of living on a dormant volcanic field is that the geology dictates the infrastructure, the municipal water supply, and the hazard planning of an entire region. In Mount Gambier, a city of roughly 30,000 people in South Australia's southeast, the drinking water does not come from a distant dam or a river offtake. It is pumped directly out of the crater of Blue Lake. The lake holds an estimated 36 million cubic meters of water, replenished continuously by regional groundwater migrating through the karstic Gambier limestone. Every resident turns on a tap fed straight from the vent of a Holocene volcano. That water balance is fragile. Because the limestone is porous and riddled with sinkholes, cave systems and solution channels, surface runoff enters the deep aquifer within hours rather than years. In the 19th and 20th centuries, early industrial and agricultural operations treated sinkholes as convenient rubbish dumps and drainage portals. Modern environmental monitoring by the South Australian Environment Protection Authority and SA Water tracks nitrate levels and chemical runoff constantly, because any contaminant that enters the karst system flows straight toward the municipal supply sitting in the crater. Further east across Western Victoria, the volcanic legacy forms the foundation of the state's agricultural wealth. The volcanic plains shire councils, from Corangamite and Moyne to the southern Grampians, sit atop rich basaltic vertisols and ferrosols. The stony rises, formed by chaotic basalt block flows, resisted early colonial ploughing and preserved native vegetation corridors, while the adjacent ash fields yielded prime cropping and grazing land. The Victorian dairy industry and fine wool production in the Western District exist precisely because basalt and scoria weather into highly productive, nutrient-dense soil. The deeper structural consequence is seismic and geothermal activity. The Australian continent is under high tectonic compressive stress as it pushes northeast against the Pacific and Eurasian plates. Geoscience Australia monitors a persistent background of intraplate seismic events across southeastern Australia. Deep fractures associated with the Newer Volcanics Province continue to release strain, producing minor earthquakes and maintaining elevated geothermal heat flow gradients in the Otway Basin. Geologists exploring hot sedimentary aquifer systems in the region have recorded geothermal temperatures exceeding 100 degrees Celsius at depths of just 3 to 4 kilometres. Hazard assessments published by Geoscience Australia and State Emergency Services categorise the Newer Volcanics Province not as an extinct field, but as an active intraplate volcanic province with a low but non-zero probability of future eruptions. Because monogenetic volcanic fields do not erupt from the same vent twice, any future ascent of magma will not emerge from Blue Lake or Mount Shank. It will punch a new pathway straight through the limestone and pasture at an unpredictable location. Emergency management agencies and volcanologists model this scenario based on past phreatomagmatic behavior. Rising magma intersecting shallow aquifers will create explosive steam blasts, localized ash falls, and scoria dispersal across regional transport corridors, disrupting the Prince's Highway and regional aviation routes. For the people living between Melbourne and Mount Gambier, the volcano is not an abstract historical chapter. It is the soil beneath their paddocks, the road base beneath their highways, and the water in their glasses. How does this entire sequence of deep rift origins, explosive groundwater interactions, and modern everyday life come together to redefine what it means to live on the Australian continent? The final open line of this investigation is not about whether another eruption can happen, but why it took a modern reassessment of plate dynamics to see what was in plain sight. For over a century, Australian geography was taught through the framework of total continental permanence, a landmass so old and so stable that violent geological change belonged exclusively to distant island arcs and oceanic trenches. That assumption was reinforced by administrative boundaries and map sheets that divided Western Victoria and southeastern South Australia into separate state jurisdictions, splitting a single, coherent mantle thermal system across different regional surveys, water allocation plans, and cadastral registers. What kept the volcanic field unnoticed for so long was not a lack of rock, but an assumption that stability across human lifespans meant stillness across deep time. The reality beneath the grass is an ongoing process. Australia continues its 7 centimetre per year journey northeast into Asia. The southern margin continues to feel mantle shear stress, and the edge-driven convection beneath the lithosphere has not dissipated. What remains unresolved is the precise location of the next conduit. Seismologists and volcanologists cannot predict where the next magma batch will ascend through the limestone because monogenetic fields do not build persistent, long-lived central volcanic cones. When the pressure next overcomes the lithospheric overburden, it will create an entirely new vent. Right now, researchers from the University of Melbourne, the Geological Survey of Victoria, and Geoscience Australia continue to deploy sensitive broadband seismic arrays and magnetotelluric sensors across the volcanic plain to image the transition between the lower crust and the upper mantle. They are mapping electrical conductivity anomalies that may indicate pockets of partial melt 60 kilometers down. At the same time, detailed karst mapping and groundwater isotope profiling continue to trace how quickly water circulates between the surface and the deep explosion craters, race against time before industrial and agricultural contamination permanently compromises the regional water table. The map of southeastern Australia looks settled, orderly, and complete, covered in highway numbers, local council boundaries, and freehold property titles. The ground beneath it remains unfinished. Which geological feature or unexpected landscape anomaly in your own state or territory has always struck you as out of place? Or which part of this volcanic timeline surprised you most? Share your observations in the comments below and subscribe for more deep investigative geography.